So in the last couple sessions, we've talked about how we can get a lot of information from the spectrum of light from some source. If I have a thermal spectrum, I can use the shape of that spectrum to figure out what is the temperature of the object that emitted that light. If we have an absorption spectrum or an emission spectrum, depending on which spectral lines are showing up, we can kind of compare those with the spectral lines of known elements and determine the composition of the gas that made those spectral lines. Well, we're going to continue that with now looking at a property called the Doppler effect. So a Doppler effect is something that you've probably actually heard before, even if you might not have heard the name of it. It's the effect where if I have a source of a wave that's not moving, then let's say it's a sound wave for a quick comparison. If I have a source of a sound wave and it's not moving, then an observer in front of the object and an observer behind the object will hear exactly the same pitch that the source is actually emitting. However, think of the sound of a passing car. Like, try to mimic the sound right now. Sound when the car is coming towards you and when the car is going away from you. You might have done something like as it passes by, the pitch appears to change. Basically, if I have a source of sound and the source is coming towards me, the crests of those waves are kind of compressed together a little bit, leading to a shorter wavelength and a higher frequency. In the case of sound, you hear that as a higher pitch. If you're the observer over here and the source is moving away from you, well, due to that object's motion, it seems like those waves are stretched out. You have a longer wavelength and a corresponding lower frequency. This is a quick YouTube video that I found with a very brief search. Someone using their car horn to demonstrate this Doppler shift effect. So you'll notice very quickly that there's a difference in pitch when the source of sound was moving towards whoever was holding the camera. And so you had a higher frequency when the source of sound was moving towards the camera and a lower frequency once it passed by. Let's do that, last pass just again. High frequency to that low frequency effect. So again, this is probably something that you've heard for sound waves, but this also works for light as well, albeit at much, much higher speeds. So again, this Doppler shift, what it is overall is an apparent shift in the wavelength or frequency of a wave owing to the source's motion. So it's a perceived shift in a wave's frequency or wavelength owing to the source's motion. And again, in the case where the source is moving towards you, the result is a shorter wavelength and higher pitch. So let me write this down. So source moving towards you towards, let's just say you or whoever is doing the observing. If the source is moving towards you, that leads to a shorter wavelength or maybe I should say it like this. It shortens the wavelength and increases frequency. If the source is moving, so if the source is moving away from you, that lengthens, that increases the wavelength. That shouldn't be there. That's very poor grammar. Okay. So we saw this specifically in the case of sound waves, but this actually does work for light waves as well. One of the key differences is light travels far, far faster than sound does. So in order to see this effect to an appreciable, noticeable effect, you'd have to be moving much, much faster to actually be able to see it yourself. But we do have the same property. If the source of light is moving away from you, that's going to increase the wavelength of light that the observer perceives. We call this redshift. So if the source is moving away, that increases the wavelength, and we call this a redshift. If the source is moving towards you, that shortens the wavelength, and we call that a blue shift. Now, these names are a little bit of a misnomer because redshift and blue shift doesn't mean that the light necessarily turns red or that the light necessarily turns blue. It just means the wavelengths are getting longer for redshift or the wavelengths are getting shorter for blue shift. Because we can have beams of light that are not even in the visible part of the spectrum being red shifted or blue shifted. It always just has to do with, is the wavelength of that light getting longer or shorter based on what was originally emitted. So for example, if we draw our spectrum again, so talk about gamma rays, X-ray, UV, visible, infrared, and radio waves. And again, in that visible part of the spectrum, we go from blue to red. If I have, let's say, some green light and the source is moving away from me, well, then that green light, it's going to shift to longer and longer wavelengths, and it might make that wavelength actually look more red. If it's moving even faster, it might shift all the way past red and into the infrared part of the spectrum, so we wouldn't even be able to see it. Or if I started with, let's say, ultraviolet light, and that source of light is moving away from me, that light that was invisible to our eyes might be redshifted so much that it actually pushes it into the visible part of the spectrum. Again, this redshift and blue shift doesn't necessarily mean that the light ends up as red or ends up as blue. It's just saying the wavelength is getting longer for redshift or the wavelength is getting shorter for blue shift. But I know we want to know, how do we quantify this? So there's a mathematical relationship that tells us how fast a light source is moving towards us or away from us based on how much one of these wavelengths is shifted. So this is our Doppler shift equation, and let's list this out and go through some of the details. So we have V equals lambda shifted minus lambda rest over lambda rest times C. Okay, so what do all of these terms correspond with? So this is how fast the source is moving. How fast source is moving. And for this equation, this radial velocity, I should say that how fast the source is moving directly towards us or directly away from us. This is going to be positive if moving away. And negative if it's moving towards us. Okay. This shifted wavelength, this is the wavelength of light that we observe. We are watching this object, and when that light gets to us, this is what we actually observe that wavelength of light to be. So this is the observed wavelength. So the wavelength of light we see. The rest wavelength is the wavelength that was originally emitted. So wavelength originally emitted. And c is the speed of light. Speed of light, which again, there's a couple of ways that we can describe this. This can be 3 times 10 to the 5 kilometers per second, or 3 times 10 to the 8 meters per second. You can use either one of those that you want, but if you use this value, your final value for how fast the source is moving would be in kilometers per second. If you use this value, your final result for how fast the source is moving is going to be in meters per second. For the calculations that we're going to do here, I'm going to stick with the 3 times 10 to the 5 kilometers per second. Sometimes we talk about the ratio of how fast is this object moving compared to the speed of light, c. And this ratio is what we call the redshift of an astronomical object. We'll talk about this redshift value specifically later on in the course when we look at how galaxies are moving, and especially how distant galaxies are moving relative to us. So the basic idea with this equation is, if I know what light was originally emitted, the rest wavelength, and I know I can measure what is the wavelength of light that I see when we detect this light, then we can go through this calculation and figure out how fast towards us or away from us is this particular object moving. So again, by using the properties of light and by using this spectrum of light, we can actually determine how fast an object is moving, again, towards us or away from us. But there's a question about this that you might be asking. Well, we can observe this shifted wavelength of the light. That's literally, the light reaches our telescope, we send it through a spectrograph like the ones that I was using before, probably better quality than that, but we send it through a spectrograph, we look at where that light is, we can measure its wavelength. But how do I know what the original rest wavelength would have been if we can't actually observe the light at the source? Again, we're going to be using this to try to determine the speeds of distant stars or, very, very distant galaxies. How do I know the wavelength of light that was originally emitted? It would be really, really helpful if we had some sort of reference wavelengths, or maybe a set of reference wavelengths that we know lots of systems like to give off. Well, let's think about those spectral lines that we were talking about before. We said in the spectroscopy session that every kind of element has its own unique spectral fingerprint. It will give off and it will emit and absorb a specific set of wavelengths. So if we look at the wavelengths of, say, hydrogen, the spectral lines of hydrogen, and let's say we know where those spectral lines show up for our sun. Again, our sun isn't moving towards us or away from us very quickly, so we can basically say that this one is essentially at rest. But if I look at some galaxy that's further away, and I notice all of those common spectral lines, they all have the same spacings, but all those spacings are just shifted a little bit. Well, we can determine that, they still correspond to the same elements, and we know the wavelengths that each of those spectral lines are actually produced at. So we look for this Doppler shift in the full set of spectral lines for some element or a bunch of different elements to try to get as much reliable information as possible. So the fact that different elements will give off this very unique set of spectral lines we can use that and basically just say, oh, I got the set of spectral lines and they're all shifted by this much. And then we can get very high accuracy measurements on exactly how fast this source is moving. So this is basically where we get our reference rest wavelengths from. So let's look at a particular example. Suppose a spectral line for a specific element is measured in the lab at 670.7 nanometers. The same spectral line for the same element appears in a star spectrum at a wavelength of 670.1 nanometers. And what could we say about this star? So pause the video and see if you can answer this particular question about how we think this thing's moving. Okay, so this wavelength that we measure in the lab, this would be our rest wavelength. Now, this particular kind of element, when it's at rest, will produce this kind of light. So this would be our rest wavelength. And then when we look at this star, we see this wavelength now being shifted to a shorter wavelength. So we've gone from a longer rest wavelength to a shorter observed wavelength. Well, if that wavelength is being shortened, that means we're going to have a blue shift. And if it's a blue shift, that means the source has to be moving towards us. This star, at least part of its velocity, is moving in our direction. So this one would be it's moving towards us. And let's actually go a step further and say, how fast would this object be moving towards us? So we're going to do a bunch of these calculation examples in here. But let's just start with our equation. Minus lambda rest over lambda rest times the speed of light. So, well, again, the shifted wavelength is the one that we see in the star's spectrum. So in this case, it would be 670.1. The rest wavelength is what was originally emitted. And again, for this particular element in the lab, that's emitted at 670.7 nanometers. We have that rest wavelength again, 670.7. And the speed of light, I'm going to use 3 times 10 to the 5 kilometers per second. Okay. When you're plugging this into your calculators, I do recommend doing this in multiple steps. If you try to plug in this whole thing at one time, there's a pretty good chance that your calculator might do order of operations incorrectly, and that's going to lead to some errors. So what I recommend doing first is just, well, let's do the subtraction on the top. So 670.1 minus 670.7 is negative 0.6 over 670.7. Then now let's do the rest of this multiplication. Let's actually do this part of the division first. So negative 0.6 divided by 670.7. I got negative 0.00089. And if I multiply that by the speed of light, 3 times 10 to the 5 kilometers per second, I get negative 268 kilometers per second. Couple of things to note about this. That negative sign just means, oh, this thing is moving towards us. When you use this equation, if you get a positive value, that source is moving away from us. If you get a negative value, that source is moving towards us. And again, if we're using this 3 times 10 to the 5 kilometers per second, then our final answer is also in kilometers per second. Let's do a couple more example calculations of this. And again, this kind of Doppler shift effect is used in a lot of different cases. So let's say there's a star orbiting around another star, a binary star system. If we can look at the wavelengths of that, then sometimes when the star is moving towards us, that light will be blue shifted to shorter wavelengths. Then when the star is moving away from us, it's going to be red shifted towards longer wavelengths. And if we observe that changing in the wavelengths of these spectral lines, we can determine how fast that those objects are orbiting around each other. So we can do this with galaxies that are rotating. We can say, well, one side of the galaxy is moving towards us. The other side of the galaxy is rotating away from us. So they're going to experience different values for the Doppler shift. So let's try this one. A sodium line in the solar spectrum is observed very close to their laboratory or rest wavelengths of 588.995 nanometers. The same sodium line is found in the spectrum of a distant galaxy, but at 630.225 nanometers. So first, let's try to answer, does this galaxy appear to be moving towards us or away from us? This is the light that was originally emitted. This is the light that we see in the spectrum of this object. This is what's observed. We're going from a short original wavelength to a longer wavelength that we observe. So that seems to be the wavelength is increasing. So that's a redshift. The source is moving away from us. But let's try to actually do this calculation to figure out how fast this galaxy is moving. So we're still going to be using this same equation. And let's see what information we can set in here. So again, the shifted wavelength is what we see in the spectrum of this distant object. So this would be 630.225 minus the rest wavelength is what this particular element would normally emit light at this particular wavelength. So that would be our rest wavelength, 588.995. Again, divided by the rest wavelength, 588.995, times our speed of light, 3 times 10 to the 5 kilometers per second. Again, the most common errors to make are switching when you're using the shifted wavelength, when you're using the rest wavelength. So make sure you're being careful in when you're using each of those wavelengths in which part of the equation. Again, I recommend when you're actually going through the calculation to break it up into parts. So let's just look at what's in the numerator here. If I take this difference, I got 41.23. So this is 41.23 over 588.995 times our speed of light. If I just do that division part, 588.995, I got very close to 0.07, just putting in 3 significant digits for that, because again, on Lon Kappa, it will want you to use 3 significant digits for all calculations, so make sure you're using that throughout the calculations. And if I multiply this by the speed of light, I get 21,000, pretty much exactly 21,000 kilometers per second. This value is positive, so the object would be moving away from us. We have a redshift in this case. So again, by using these spectral lines and seeing how these spectral lines are shifted, and how these sets of spectral lines are all shifted from the same reference point, we can use that to identify what was the original wavelength. We can observe the new wavelength, and we can use those together to determine how fast is this object actually moving. Now, these are spectras of actual galaxies. This would be an example of an emission spectrum. We have, not a lot of light, but every once in a while there's this big upward spike, and some of these upward spikes are associated with hydrogen. Remember when we saw the spectral lines of hydrogen, this line right here corresponds with the red line that was in the spectrum of hydrogen. This one right here corresponds with the teal line in the spectrum of hydrogen. And on this graph, if we have this particular spectral line, we can kind of scroll down to the bottom and identify, well, what wavelengths are these occurring at? For this particular galaxy, they're pretty much at their original rest positions. This galaxy is not moving very fast relative to us, at least compared to many of the other examples that we're seeing. So this red hydrogen line, this teal hydrogen line, they're at pretty much their ordinary rest positions. However, in this example, that red line and that teal line have both been shifted a certain amount. So if this one is pretty much not moving relative to us, this one, notice those wavelengths have been shifted to much larger wavelengths, much longer wavelengths, which corresponds to a lot of redshift. So let's go through this one and see if we can identify how fast these galaxies are moving. We've already said that it's shifting from to longer wavelengths. So we have a red shift. The source is moving away from us. But let's figure out exactly how fast this source is moving away from us. So we're still going to be using this equation. And let's start setting up some parts. So to begin with, we need to identify what is the shifted wavelength. Let's focus on this hydrogen alpha line. Okay. If I pick this wavelength, that seems to be showing up right around, I don't know, pretty close to 8,000 angstroms. And 8,000 angstroms, remember in one of the previous sessions, we talked about angstroms. Just for a reminder, 10 angstroms equals 1 nanometer. So if this is showing up at around 8,000 angstroms, that would be about 800 nanometers. And this is the spectral line that we actually see coming from this object. So that shifted wavelength would be 800 nanometers. The rest wavelength, well, for this hydrogen alpha line, that rest wavelength is 656.3 nanometers divided by the rest wavelength, 656.3, and then multiply that by the speed of light. Well, again, at this point, once we've identified what is the shifted and what is the rest wavelength, the rest is kind of just running the numbers. So 800 minus 656.3 is, I got 143.7. Then doing the division portion of that, divided by 656.3, I got 0.219 times the speed of light. So multiplying that by the speed of light, I got this galaxy is moving away from us because it's a positive value, away from us at 65,700 kilometers per second, approximately. So this galaxy is moving away from us at quite a large clip. But that was using the hydrogen alpha line. What if we did the same sort of thing, but instead of using the hydrogen alpha line, sorry, the red hydrogen line, they have different names. I apologize for using that notation without saying it. The red hydrogen line is how we got that number. What if we looked at the teal hydrogen line? Well, in this case, that teal hydrogen line seems to be showing up at around, it's a little under 6,000. Let's call it 5,900 angstroms. I'm going to make a new section down here. So if this is the shifted wavelength at around 5,900 angstroms, well, it's 10 angstroms per nanometer. So if it's 5,900 angstroms, that would correspond with 590 nanometers for that shifted wavelength. The original one, if we're looking at the teal line, was 486.1. And that's what we see in the original spectrum if it's not moving. Rest wavelength on the bottom. And we've got the speed of light, 3 times 10 to the 5 kilometers per second. Again, let's run through the numbers. So the shifted wavelength minus the rest wavelength. I got 103.9 over 486.1. That division divided by 486.1, I got 0.214, 3 times 10 to the 5. If I multiply that by the speed of light, I got 64,100 kilometers per second. Again, there is a little bit of, I wasn't exactly on 5,900 angstroms. It was a little bit larger than that, so this is probably a bit of an underestimate, but notice that they match up pretty well with each other. So again, the idea here is that based on this Doppler shift effect, if I see some of these wavelengths of light from elements that I know what their original spectral lines are, if I see some of these wavelengths shifted to longer wavelengths, I know the object is moving away from me. That's a redshift. If those wavelengths are being shifted to shorter wavelengths, well, I know that object is coming towards me. It's going to have a blue shift in that case. And this allows us to look at the spectrum of light from these distant objects and figure out properties of their motion. So this is just another one of those ways that we can learn a huge amount of information by looking at the spectras of light from these distant objects.